Now we're going to consider blood types. There's 4 different blood types. Well, in addition, there's also positives and negatives. We're going to consider blood type as our variable. It's a categorical variable where you have either AB, or O, the universal donor. We're going to use relative frequencies, which means percents, from large samples of randomly chosen individuals, and we can estimate the probability of choosing a person with a given blood type. Using relative frequencies, the Stanford University's Blood Center gives the following probabilities of human blood types in the US as the following, which is given in the table. Notice that if you added all of these up, it would add up to one whole, and each probability is greater than or equal to 0 and less than or equal to 1, which means it is a valid probability distribution. The most probable blood type is the one that shows up the most, which would be O, and the least probable is AB. If we considered 100 people, how much would we expect to have of each blood type? You would just then multiply this by that sample size of 100. You would get 45 for O, 41 for A, 10 for B, and 4 for AB. Do we really expect that exact number? And this should be of 100 so that it matches question 3. No, we do not expect exactly. That doesn't mean if the first 4 people you talk to are AB that they have nobody else can be AB. It's chance, it's probability. It's not certainty. This is no. If we considered 1,000 people, how many can we expect? Well, again, you would just then multiply this by 1,000 instead of 100, and you would get 450 for O, 410 for A, 100 for B, and 40 for AB. Boreal owls are common in Canada and Alaska. They're fairly small, averaging 10 inches in length and weighing from 4 to 6 ounces. And they make their nests in woodpecker holes. The number of eggs that a nest generally has ranges from 4 to 6 eggs. And then we're going to use relative frequencies from a large field of observation to estimate certain probabilities. Here is the distribution that's given. Again, you always want to check your distribution to make sure that all of the values are between 0 and 1 and that they add up to one whole. Otherwise, it's not a complete probability distribution. Which is more likely, finding 0 eggs or 4 eggs in the nest? Well, here's 0 eggs and here's 4 eggs. More likely would be a greater probability, which would be 4 eggs. Now, which is more likely, finding 4 eggs or 5 eggs in the nest? Again, 0.25, 25% is bigger than 5%, so 4 eggs. Lastly, which is more likely, to find 1 or 2 eggs. Here's 1 and here's 2. Well, those are equal, so neither. They are both equally likely. And now, a few things to consider about probability. There's certain characteristics of a probability distribution. I talked about this just a little bit when mentioning whether something's a distribution or not. All outcomes are random events. All outcomes are assigned a probability. The probabilities are numbers between 0 and 1, and the sum of the probabilities has to equal to 1. A probability could be 0, and it could be 1. That is something that does happen. Like if it never occurs, it's a probability of 0. If it always occurs, it's a probability of 1. You can add probabilities. If I wanted to know what's the probability of being a Republican or a Liberal Party member in Napa County, I could add up all of the Republicans, add up all the Liberal Party members, and that would be the probability. These are what we call or problems because I said what's the probability of being a Republican or a Liberal Party member? And you can add these probabilities if you're dealing with disjoint data. And disjoint data is data that is mutually exclusive, which means it can't happen at the same time. You can't be a Republican and a Liberal Party member at the same time. Maybe you can, and it could be a bad example, but you're looking for things that can't happen at the same time. Like if I have a bag of marbles, I can't have a blue marble and a red marble at the same time. It's either blue or red, unless you, again, are doing a mixed color, but you need to be clearly defining your variables. Otherwise, you need a new plan. So right now, we don't have a plan for how do you add probabilities that are not disjoint. Think about the context of a problem. It's really important. A lot of times people will just perform calculations, not paying attention to what's going on, and they'll apply a formula that doesn't even make sense. There is, every year that I do a probability chapter or section, the calculators, if you multiply your probabilities, will sometimes come up with numbers that look like this. And so students will say, well, the probability is equal to 1.23. Well, that doesn't make sense. You cannot have a probability over 100%. It's either going to happen all the time and be 1, or never going to happen and be 0, or somewhere in between. It can't be greater than that. This is this is using scientific notation, which is a number that is very small, and our calculator just shortens that number so it appears in the window. So you need to be on the lookout for this. If you have a calculator and it gives you a number bigger than 1, you need to be able to recognize and go, oh wait, that's in scientific notation, that's not right. So you have to consider context when you're working these problems out. You can subtract probabilities, and this happens if we want to answer not questions. For instance, review the blood data where you're talking about type O blood. Type O was what, 45%? The probability of not having type O blood would be 55% then, because you're talking about the whole population minus the type Os. We call these complement problems. Now let's move on to Module 15 section, or now let's move on to Module 15 Part 2. I'm going to pull some of the data that we used from Module 14 here. First of all, defining independent events. Independent events are two events where it doesn't matter whether or not one happens in terms of influencing the other. For instance, whether I go to work or not has no impact on whether it's going to rain or not. They're not related. But whether I go to work or not probably has to do with how my health is. If I'm sick, I'm probably not going to go to work. So those two would not be independent events. Independent events do not have a relationship, and one does not influence another. Whether I get a 2 on a die does not influence rolling it again and getting a different number, because each time is equally likely to happen. Those are independent. But dependent events, like let's say I have a deck of cards and I pull out a card, that's going to impact what happens the next time, or the probability for the next time. So those are things you need to consider. The probability to select a student at the college is in the art sciences program. We have 4,660 out of 12,000. And you can write your answer as a fraction or a decimal depending on how the question is worded and what your answer choices look like. Like if the answers are decimals, then you want to put your answer as a decimal. If your answer choices are percents, you want to put them as a percent. The probability that a randomly selected female student is in the arts and science program. So female, that's 4,660 out of 8,994 arts and science program students. Because this is saying selected student at the college, that was the total, arts and science. Now we're talking about females in the arts and science program. So those are two different situations. That divides out to be 0.5181. Now, is whether or not you're in the arts and science dependent on whether or not the student is female, why or why not? If they were independent, the probabilities would be the same. It wouldn't matter if I was a student in the college or if I was a student in the arts and science program, the percentages would wind up being the same. But because they're not the same, their probability is different, they are dependent. Meaning that there are more students in the arts and science program than there are females in the arts and science program. So here there's a 75% in arts and sciences, but females is only 51%. That would be 75 and 75 together. But we're not going to get bogged down with formulas given that relates to joint marginal and conditional probabilities. We're not going to use them for this course, so we're just going to rely on finding conditional probabilities from a table. There is a formula for how you find conditional probabilities, but again, it's not something we cover in this course. Discrete and random variables. A discrete variable is a variable that is listed and can be counted, like number of shoes in my closet, number of hours that you're taking at the college, number of credit hours, I should be specific, the number of credit hours you're taking at the college. Continuous random variables are variables that are numeric that can be any number on an interval. For instance, your temperature. You can't go from having a normal temperature of 98.6 to a temperature of 102 without reaching all of the temperatures in between. That's continuous. All right, did I get this on page 95? Determining whether something is continuous or not. So again, if it's discrete, you can count it. And if it's continuous, it can take on the range of values. So the number of courses you're taking, that's discrete. Your height is continuous because again, you have to reach, you don't all of a sudden go from being, 4 feet to 6 feet without reaching all the heights in between. Your exact body temperature is continuous. The number of siblings is discrete. You have one, you have two, you have three, and half siblings, and I always get smart aleck answers, but half siblings are siblings. That counts as one whole. The exact time the student spends doing schoolwork a week is continuous. And the number of alcoholic beverages that the student drinks in a typical week is discrete. And I'm not asking you for the number of 4-ounce glasses or whatever. It's just, did you drink one? Did you drink two? And whether you finished it or not, things like that aren't considered. We're not trying to make it hazy. It's just 1, 2, 3, and so on. Okay. The probability distribution from the owls that we just recently worked with is a discrete random variable because we can talk about the number of eggs. There's either 0, 1, 2, 3, 4, 5, or 6. Now remember, to be a probability distribution, each probability has to be between 0 and 1, and the total has to be one whole. So all of these have to add up to one whole. So that's 0.2 plus 0.1 plus 0.1 plus 0.25 plus 0.25 plus 0.05 plus something has to equal one whole. If you add these up, that's 50, 60, 70, 80, 90, 5. That is 95%. So the missing value would be 0.05. And it's unusual. Unusual, I would say, is about 5% or less. So it would be unusual to find 5 eggs or 6 eggs in the nest. Those are unusual. Now, considering the probability histogram to get a visual sense, we're going to put a column of data into StatCrunch for the number of eggs and then another of data for their probabilities. And we're going to use this to find out our expected value and our standard deviation. So you're going to put eggs in var1 and you're going to put the probability in var2.